Hello, everyone. Welcome once again to our cycle of seminars of the Astronomy Department of the IAG. Today, we have the pleasure of having with us Professor Paramita Barai. We are really glad to have her here with us. So Paramita, thanks a lot for accepting our invitation to be here with us, sharing your research. So Paramita got a degree in electronics and electrical communication engineering from India Institute of Technology, Kharagpur. And she got his master and PhD degree in physics and astronomy, both from Georgia State University in the US. She worked as a postdoc researcher in several institutes around the world, like in the University of Laval in Canada, the University of Nevada, Las Vegas, US, in the Osservatorio Astronomico di Trieste in Italy, and in the Scuola Normale Superiore di Pisa, also in Italy. And since 2017, she's a FAPESP Young Researcher at the IAG, and most recently at UNICSUL. And this year, she became a visiting professor at Universidade Federal do ABC. Her research is focused on cosmology, formation and evolution of galaxies, black holes, and AGNs. And today, she will talk about coevolution of central massive black holes and host galaxies. And well, like always, I will ask everyone to please turn off your microphones and your cameras during the presentations. And the questions will be done after. And if you have a question, please indicate this in the chat, both in YouTube or here in the Google Meet. So whenever you want, Paramita, you can start sharing your screen.
Okay, so once I go to the presentation mode, I will not be able to see any chat. So only at the end of the presentation, I can answer.
Yes, don't worry. Yes, okay. Yes, don't worry. We will keep an eye on that. Don't worry.
Okay, thanks, Maria, for the invitation. And can you see? Okay. Okay. So as Maria said, that I'm currently, from this September, a visiting professor at the Universidade Federal do ABC. And today I will talk about my continuing research on evolution of central black holes in galaxies. So a fraction of all galaxies are seen to contain an active galactic nuclei, or AGN. These are yes. It is, yeah, it is giving me some problem. Let me see if I have to restart. Can you see now? Okay. Yes, yeah. Yeah, I will do it. Okay. So yes, so AGN are the galaxies where we observe that the central region radiates a large amount of energy as compared to the rest of the galaxy. And we believe that there is a supermassive black hole located in the very central region of the AGN of mass between 1 million and 1 billion solar masses. And the gas around the black hole is accreting into the black hole, and there is a release of gravitational energy. And this energy is being emitted out in various forms. For example, outflows are observed in many different wavelengths coming from the AGN. And the most impressive of them are the very huge radio lobes and the radio jets that we observe in some of the AGN. And we also observe them in other wavelengths like UV and X-ray. So This is called feedback, this energy distribution from the center. So this energy output from the central supermassive black hole is distributed to the surrounding. And in this way, the black hole existing at the very central of a galaxy, it affects the rest of the galaxy. In this way, it impacts the star formation in galaxies. There can be two forms of the feedback. And in my work, I focus on the negative form of feedback, where the star formation is quenched or reduced by heating the gas in the galaxy or by expelling the gas out of the galaxy. And in this way, the feedback from the central black hole, it affects the number of galaxies by having this negative feedback. Whereas we should also remember that feedback can be positive, where star formation is actually triggered by the expansion of the jets. And in this way, the jet compresses the cold clouds in a multi-phase interstellar medium of the host galaxy. But for my talk today, I will focus only on the negative feedback, where the black hole quenches star formation in the host galaxy. So there is kind of a cyclic process in this way, where the host galaxy, it regulates the amount of gas which flows into the black hole, and in this way it affects the black hole accretion. And in turn, the black hole outputs this energy and it affects the star formation in the galaxy. So there is kind of a coevolution going on in a cyclic way of the host galaxies which have a supermassive black hole at their centers. And this creates several correlations between the central black hole properties and the host galaxy. The most important is the black hole mass versus the, as shown in the figure here, black hole mass versus the stellar mass of the host galaxy, or it can be black hole mass versus velocity dispersion of the host galaxy. And this also affects the number of massive galaxies, because the feedback, it expels the gas, and so it prevents the formation of very massive galaxies. And this affects the luminosity function of galaxies. So there is a reduction in the number of very massive galaxies in the high luminosity end. And this is thus an important ingredient in galaxy formation models to bring the theoretical luminosity function in accordance with the observations. So we call this scenario as the galaxy black hole coevolution, in which the galaxy affects the growth of the black hole because it controls the amount of gas which falls into the black hole. And as well, the black hole affects the star formation in the galaxy because it either expels the gas or it heats the gas and does not allow the star to form. So it results in a self-regulated black hole growth. And in observations, we find that there is a correlation between the star formation rate and the number density of AGN, the cosmological evolution of these quantities, and they both peak at similar epochs between redshifts 2 and 3. Okay, so my work also focuses on intermediate mass black holes. Now, in observations, black holes are mostly observed to be either stellar mass, or the black hole mass is less than 100 solar masses, or supermassive, which are the black holes that I said until now, or mass greater than 1 million solar masses. Now, what about the population of intermediate mass black holes? This has not been observed so much as the other two populations, but very recently, these intermediate mass black holes have started to be observed at the centers of dwarf galaxies. So dwarf galaxies are the small mass galaxies, and so naturally we expect the black hole at their center to be smaller than the intermediate mass, smaller than the supermassive black holes. Now the question is how many of them have it, and it is always difficult to observe because the dwarf galaxies are the low luminosity ones, and it is much more difficult to observe them rather than the supermassive black holes. So, for example, this figure shows the black hole mass versus the stellar mass. And these black holes at the low mass end are between 100 and 10 to the power 5 or 10 to the power 6. We see that there is a small population. These are the intermediate mass black holes at the centers of dwarf galaxies. And of course, as you can see, the number here is much smaller than the supermassive black hole, which populates the high mass end of the M black hole M stellar relation. So in one of my recent papers, we performed cosmological simulations to probe these intermediate mass black holes. And we tested if they would grow at the centers of dwarf galaxies. And also we tested the impact of the feedback on star formation. So before going to the methods that we use, I will just give the motivation that what we are trying to study in a cosmological hydro simulation. So we see around us galaxies of many different shapes and sizes, and from observations of several different observations, we know that now the age of our universe is 13.7 billion years. And we observe galaxies at older and older epochs. And the most oldest observation of the universe that we have is given by the second panel here. It is the cosmic microwave background radiation. This is an epoch when there were no galaxies and no structures. It was just at the beginning of the evolution. And this is, models predict that this was at 380,000 years after the Big Bang. So we have observations that at this epoch, and from here we want to study how we see all the galaxies in the current epoch of all the different shapes and sizes, and as well as the black holes in them. So the idea is that there were primordial density fluctuations that happened. This is all theory because we cannot probe this very early epochs before the CMB. There were primordial density fluctuations caused by some quantum perturbations, and these were expanded by inflation, and these became macroscopic. And some slightly overdense region collapse, and the slightly underdense region, they undergo expansion. So there is gravitational clumping from these initial density fluctuations. And then the structures like stars, galaxies, clusters, they all form from these density fluctuation and the gravitational clumping of matter. And the main forces which affect The evolution is gravity, which affects both dark matter and baryons, and hydrodynamics, which affects only baryons. I will come to the dark matter in the next slide. Okay, so cosmological hydrodynamical simulation is a methodology to study this evolution of the universe, starting from the density fluctuations at the epoch of the cosmic microwave background, and then forming the first stars, then slowly the galaxies, and then up to today, all the different galaxies that we see around us. So in such a simulation, we simulate a region of the universe containing many galaxies. The initial condition is the cosmic microwave background, and so it is like a density field, and the primordial density fluctuations are assumed to be Gaussian, which is what we observe from CMB, various different probes of the CMB. So the initial condition is 13.7 giga-year ago, close to the Big Bang. And also from these observations of the cosmology, we know that our universe consists of dark matter and baryons, and as well as dark energy. So we call it the lambda cold dark matter model. And these are used as parameters in the cosmological simulations. So we follow both dark matter and baryons. So the main force is gravity, which affects dark matter as well as baryons, and hydrodynamics, which affects only the baryons. And in this way, we start with the initial condition and evolve from the epoch of the CMB, which is at redshift of 1000, up to the present epoch, or redshift 0. So this is a 13.8 giga-year of evolution. And that is why it is very computationally expensive, because we want to study the large-scale structures, and as well we want to study the galaxies inside it. So the code I'm using is a modified version of the Gadget 3 code. It has a 3 PM method to follow gravity and a smoothed particle hydrodynamics to follow the hydro, and originally written by Volker Springel. And within this, we have all the recipes of star formation and galaxy physics as sub-resolution physics. Because the scales involved are the box that we are evolving is very large. However, the physical processes occur in much smaller scales. So that is why this is called sub-resolution physics. And each of these involves a lot of details, and I am not going through them. So if there are some questions, I can answer later. For example, we have cooling and radiative heating, star formation, evolution of the stars, and origin of the chemical elements and feedback from them, as well as feedback from supernova, which is implemented as kinetic feedback. And I worked in one of my previous paper, I worked on implementing such a recipe in the Gadget code. And as well, we have accretion onto central black holes and feedback from them. And I have worked on implementing these recipes again in the Gadget code in previous papers. So here is a movie showing the evolution of density in the left panel and temperature in the right panel of a 2 megaparsec cube simulation box. And it shows the cosmic time and the redshift here. And This shows the halo mass of a halo that I'm showing here by the circle. And so we can see that initially the density was almost uniform in the box. And slowly there are the formation of these clumps and the filaments. And then the clumps merge to form larger clumps. And the intersection of these clumps is actually a galaxy. So the final time. And in the right panel, by these circles, we see several galaxies forming, which happens at the intersection of the filaments. I should say that this is a 2 megaparsec volume, so like a small box cosmological volume, and therefore there are many galaxies within this volume. Okay, moving on. So yeah, so how do we include black holes and AGN in these simulations? So we assume that when the galaxy has reached a certain limiting mass, there is a seed black hole at its center, and the location is assumed to be the minimum of the gravitational potential. So we put a seed black hole by hand at the center of every massive galaxy, and then the black hole grows by accretion of gas and by merger with other black holes. And then there is feedback of energy as it accretes gas, according to some of the equations that I will show you next. Yeah, so about the accretion, we assume Bondi-Hoyle-Littleton accretion. So this is the equation for, so in the simulation, there is a black hole particle at the center of every galaxy. And then using the gas density here, and using the sound speed, which depends on the temperature, and as well as the mass of the black hole, this quantity is computed for every black hole as soon as it is seeded. And then we assume a limit of the Eddington rate. So we do not allow the black hole to grow beyond the Eddington rate. And this gives us the black hole accretion rate. And then we assume this radiatively efficient accretion with an epsilon r equal to 0.1. And some of this radiated energy is fed back and coupled to the surroundings. So we have two efficiency parameters here, epsilon f and epsilon r. We keep the epsilon r fixed to 0.1, but this epsilon f is a parameter variable in our simulations, and we usually tune it to make the simulation in accordance with observations. And then using this E feed dot equation here, we equate it to the kinetic energy of an outflow. So we use this equation, and then again, using this form of the E feed dot, we have a relation of the mass outflow rate in terms of the black hole accretion rate. This black hole accretion I defined here as the minimum of the Bondi and the Eddington rate. So for every black hole particle, these quantities are computed. So the accretion rate gives the outflow rate, and that is implemented in the simulation by kicking some gas particles around the black hole. So we use a probabilistic method, and then again, this quantity is computed for every black hole particle. And finally, we give a velocity, we compute, so the center here is the black hole particle, and we compute the particles in a bicone volume like this. And if the probability is less than this, then we give a kick according to this equation. So we increase the velocity by certain amount. This VW is again a kind of a free parameter, which we tune to make the black hole growth in according to the observations. And yeah, so this is basically the prescription for the kinetic feedback from AGN, which I included in the gadget code in according to which was published in this paper. Okay, so I think I have to. So this is a movie showing the overdensity of gas, and the red circles here are the black holes. So you can see, and the size of the black hole is proportional to the radius of the circle. And you can see that they are merging. Initially they are small, but they merge with each other, and as well they grow by gas accretion, and they become larger and larger. And in the end, we have several supermassive black holes at the center. And this is actually an outflow, low density outflow, which is created by the black hole. I will not show this because the movie played. Okay, here I'm showing the impact of AGN feedback on producing an outflow. The left column here is a run with no AGN, whereas the two right columns are with AGN feedback. And especially for this right column, we see that a very strong outflow is created here as the low density region, which is not found in this case. And this outflow is hot, as shown by the temperature map in the middle row. So low density, hot outflow. And the bottom panel, it shows the projection of the star formation rate of the gas. And we also see that there is no star formation because this gas is heated to a high temperature, or some of it is expelled out. So the star formation is also less with the AGN feedback. Okay, so this is a plot showing the black hole mass versus the redshift of some intermediate mass black holes. And in these, the seed mass is around 100 to 1,000 solar masses. And we find that they are seeded around redshift 20 to 15, and then they grow up to redshift of around 4, and they have become the high mass end of the intermediate mass, or the low mass end of supermassive black holes. So this is actually a result from the Barai and De Gouveia d'Alpino, where we showed that starting from stellar mass seeds, we can grow intermediate mass black holes at the centers of dwarf galaxies. And this is actually my previous paper, where I study supermassive black holes. So here we start from 10 to the power 5 solar mass seeds, so kind of here in the intermediate mass, so high end of the intermediate mass. And these black holes, by redshift 6, we can grow up to 10 to the power 9 or billion solar mass black holes. And this is the star formation rate density. So we see that whenever there is a high growth of the black hole, so all these curves are different runs. And this blue curve here is where the black hole is not growing very much. And there is also a dark blue, which is the supernova only case, where there is no black hole. And for all the other runs, we see that whenever the black hole is growing, we have a quenching of star formation already at a high redshift. And we see the similar behavior in the supermassive black hole case. Okay, so now I will show some very new results. So I have been doing some recent 50 megaparsec cube simulations, starting from redshift 100 up to redshift 0, or the whole 13.8 giga-year of the universe is evolved in these. So these are, I would say, moderate resolution, because we use 256 cube dark matter and an equal number of gas particles. So the dark matter particle mass is 10 to the power 8, 2 times 10 to the power 8 solar masses, and the gas particle mass is 4 times 10 to the power 7 solar masses. And the softening length is 3 kiloparsec. Yeah, this issue of the resolution is the most challenging, because we want to study the whole region of the universe with many galaxies, but at the same time, we want to probe what is happening inside the galaxy. So there is always a compromise between the resolution that we can have and the physics that we can study. So here, showing images of the density in the top panel and stellar mass in the bottom panel at redshift 6, redshift 2, and redshift 0. So at redshift 6, the universe was much more homogeneous than today, and there were much less amount of stars, and slowly by redshift 2 or 3 giga-year, we find that at the intersection of the filaments, we form stars, and they merge together to form larger clumps, which are the galaxies. And finally, at redshift 0, we have these clumps, which are the galaxies. And these are the places where there are the stars. Okay. This is again showing at redshift 0, one of this run. And here now, I have circled the virial radius of the halos and the position of the black holes. So in red circle are showing the virial radius of halos greater than 10 to the power 13 solar masses. And blue circle, okay, you cannot see, so I'll not even say. And the magenta points here are the black holes. So I have some plots about the black hole growth. Yeah, this is the black hole mass versus the stellar mass diagram of these simulations. And the blue points here are from my points taken from my simulation. And the lines here, the solid line, the dashed line, the dotted line, and the shaded region are observations, because there are high redshift observations of quasars that say that the M black hole M stellar is a little bit higher than the current value, which is shown by the black solid line here. So, okay, I should mention this, that when I seed the black hole, I seed it kind of on the M black hole M stellar relation. So whenever a galaxy reaches this 10 to the power 9 solar masses, I seed a black hole of 10 to the power 5 in this. So this is the region where the black holes are seeded. And then I let it grow according to the accretion prescription that I mentioned. And so the black holes also merge with each other, and then they have feedback. And then I see what happens as time goes on. So for example, in the top middle panel, it is at redshift 3 or of time 2 giga-year, then redshift 2, redshift 1, redshift 0.5, and redshift 0. So I think my black holes are kind of growing, probably too much, because here they lie on their relation, but here they have almost crossed this. So these are still preliminary simulations, so maybe I have to tune some of the parameters again. And yes, I have, yeah, so these are, I should say these are preliminary results. But yeah, and trying to compare, but again, from observations, this is, yeah, I show the black hole mass versus the stellar mass. So this is a completely observational result from Reins and Voluntary 2015. And I think in observations is also seen that at the high mass end, the black hole mass versus the stellar mass is a little bit higher than at the low mass end. Okay, so now showing the black hole mass versus redshift diagram of, yeah, this is one simulation and showing 6 black holes from this, 6 of the massive black holes in this simulation. And I show the cosmic time in the top axis. So starting from 10 to the power 6 solar masses, I find that there is a growth and all the black holes have reached, almost grown to their maximum mass by redshift 0.5. And after this, there is a almost, it remains almost flat. This also implies that by this epoch, the gas content of the galaxy has been finished because it has also formed stars, and there is like a passive evolution after this. Okay, so now the top right figure is actually one of the most important, or I should say relevant things that I have been trying to study, that how does the black hole mass versus the stellar mass diagram evolve with time. Because as I showed here, this middle panel, it shows the observation. But in an observation, we only see at one certain epoch. We see the galaxy and the black hole at certain redshift. We do not know that how they have evolved along, like how they have evolved, like starting from the Big Bang up to the present epoch. So a simulation like the one that I am doing is important to understand this evolution. So in this figure, the top left panel, I'm showing the stellar mass versus the redshift and the cosmic time in the top panel. Here again, I see that the galaxy has grown. Okay, so the curves are for different black holes and the host galaxy of each black hole. So this shows the mass growth of the host galaxy of each black hole. Sorry, how much time do I have, or I am already over time?
You can have 5 more minutes?
5 minutes, okay, I think I should be done in 5 minutes. Okay. So yeah, each curve is the host galaxy of one black hole. And as you can see that sometimes the black hole moves from one galaxy to another because there is a merger event, and then there can be a jump in the stellar mass, so this one and this one. But here again, we see that most of the growth, galaxy growth in the universe happens between redshifts 5 and 1 or 0.5. Well, between 1 and 0.5 is like 5 giga-year of evolution. And basically below redshift 0.5, there is almost no growth of the galaxies. So all the galaxies and the black holes have already grown by redshift 0.5. And the top right panel shows the black hole mass versus the stellar mass. And the colored curves are from my simulation, and the black lines are the observations. This is the solid line is the redshift 6, and the dashed line is redshift 0. So I find that in my simulations, at least, the stellar mass of the galaxy grows first, and the black hole has a little evolution initially, and then the black hole grows to even overshoot the M black hole M stellar relation. Okay. Yeah, and this showing the star formation rate density in solar masses per year per megaparsec cube as a function of redshift. And the colored curves are different simulations, and the dashed line here is the observation. So usually at very high redshift, the simulations are above the observation, because I guess this is some resolution issue. But in the simulation, we try to tune the parameters such that they match with the observations at the lower redshifts. Okay, so this is almost at the end. I showed the formation of a spiral galaxy, the dark matter in the top left panel, gas in the top right panel, and the stars in the bottom panel. So I will let it play again. Okay. I have to start again. Yeah, so at very high redshift, there is almost nothing because the universe was homogeneous. And slowly we see the formation of these clumps. And at high redshift, again, the dark matter and the gas is similar because there is not much hydrodynamic effect. And we also see the formation of the stellar clumps in the high dense region. But you see that the dark matter, it remains spherical because it interacts only by gravity, whereas for gas, we see these tidal stripping features because it undergoes hydrodynamics, and the dark matter does not follow the hydrodynamics. Okay, I think, yes. So finally, summarizing, cosmological hydrosimulations are a powerful tool to reproduce the observed large-scale structure and to study the evolution of galaxies over the whole age of the universe. But to do this, because we have only limited computational resources, it's always a trade-off between the time that is needed to the simulation and the physics that we can implement. So the results that I presented are basically taken from Barai et al. 2018 paper, where starting from 10 to the power 5 solar mass seeds, we grew the black holes to billion solar masses in 1 gigayear. And for this, it needed to accrete at the Eddington rate. And in the relatively recent paper, we grew the black hole to intermediate masses by redshift 6, and starting from a lower mass seed. And in any simulation, we see that star formation is quenched when the black holes grow massive, and there is also the generation of powerful outflows. And very recently, this is like a very preliminary work, not even written, and I am doing simulations of 50 megaparsec cube for the whole 13 gigayear evolution of the universe, and trying to understand how the black holes grow in the M black hole M stellar relation. And yes, that's all. And now I'm open for questions. Thanks.
Okay, thank you a lot, Paramita, for your talk. It was very interesting, very nice results. Just out of curiosity, how long does one of these simulation of 50 megaparsec cube, how long it takes one run of this simulation?
Yes, this I am actually doing moderate resolution because I know I have to do many of them. That is why I am using 256 cube. But so for me, it takes, I am doing around 100 processors. Yeah, there is also the question of scaling. So if I increase the number of processors, sometimes the time does not decrease linearly. So I am doing on 100 processors. So it takes 2 weeks in 100 processors.
Okay, a lot of time. Okay, we have questions now. The first one from Betty. Betty, you can ask your question. Hi.
Oi, Paramita.
Hi, Beth.
Excellent review. Thanks. It was very, very good. I have a couple of questions. One regards very recent results towards the growth of black holes out of merging of black holes, because this process may allow for dissipation of gravitational, production of gravitational waves, and therefore dissipation of energy through this process, the emission of the gravitational waves. And the results do suggest or indicate that in the beginning, this process of merging is very efficient, but then because of the dissipation, the time, the merging process is refrained, is decelerated greatly, and it comes that when the black hole has ground to a mass of the order of 10 to 7 solar masses, the growth time goes to a value that is larger than the Hubble time. So this is a current puzzle, you know, that we have to understand what is really going on, because we know, at least indirectly from the observations, that black holes, supermassive black holes, can grow up to 10 to 10 solar masses, right? So, but this is a current puzzle, right? That has to be solved. And besides, I know that in the cosmological simulations, the gravitational wave dissipation is not taken into account, but eventually this dissipation, this loss, has to be taken into account in order to allow for a realistic growth of the black holes. So I want to know, I mean, what might be your, comments on this, or your impressions. I don't know if you were aware of this fact. And I have
I was not aware of this. So this is from gravitational wave observation.
Not observations, but simulations, right? Calculations that show that if you take into account the losses during the merging process, because all these calculations are, of course, motivated by, the recent results from.
Okay, yeah, I think I maybe will be able to make a comment, because if they are.
The observations, I mean, the instruments that observe gravitational waves do not have still the means to observe supermassive black holes merging, not yet. But the future instruments will be able to probe these frequencies, right? So there are already projects for this. But motivated by this, numerical calculations do show, or not even numerical, semi-numerical, analytical numerical simulations do imply that this, as there is this release of gravitational waves, this, postponed the growth rates, right? So it increases the growth time of at a point that when the black hole has achieved the masses, I don't know, of this order. We have to see in detail in the papers, to go through the paper. But at the end, we may have this problem, right? So this is one point that eventually this has to be taken into account also in the cosmological simulations, right?
Mm-hmm.
In order to see what are the major constraints really, right, for in the growth.
Yeah, so my comment is this, as I understand from your comments, is the calculation was done from gravitational wave observations, which are less than 100 solar mass black holes. Now, I think the supermassive black hole, which grows up to billion or 10 to the power 9,
no, but this
will start with more massive seeds.
No, but this is the point. The calculations, when you merge, they do show that if it goes up to 10 to 7, the growth time at this point is really long, of the order of 1 Hubble time. So, but of course, we do expect indirectly from observations that supermassive black holes can grow up to 10, right? And so this is, something that is currently a puzzle that has to be explored and somehow, right?
Yes.
So this is one point. The other question is a quick question regarding the resolution of the the 50 megaparsec. Because you said that the smoothing length, therefore, at least the coarse resolution is around 3 kiloparsec.
3 kiloparsec, yes.
So this means the size of a galaxy. How do you follow the growth of black holes with this? What is the best resolution, the smoothing length that you get in the simulations?
Well, because in these we follow the more massive galaxies, because the galaxies are 10 to the power 12 or 13 solar masses.
Right. So you do not solve down scales
No.
down to 3 kiloparsec. All right. Okay. Thanks, Paramita. Again, a very nice review, very nice presentation. Thanks.
So now, Juan, you can ask your question.
Hi, Paramita. Thank you for your talk. My question is that the mass of the seed, the black hole seeds, I see that you consider, well, my question is if there is a model to motivate the initial mass in your simulations, or this is a free parameter that you are investigating?
This is a free parameter, but at the end, I want to grow the 10 to the power 9 black hole by, in one of my, in Barai et al. 2018, I will show this slide again because it will be easier to answer. So in one of my previous paper, I tried to form the high redshift quasar or grow a 10 to the power 9 mass black hole by redshift 6. And for this, I started with 10 to the power 5. And so the only constraint is that I want to so here in the top right panel, you can see that starting from 10 to the power 5, it grows up to 10 to the power 9 by redshift 6. Okay, another thing is the resolution, because my gas particle masses are around 10 to the power 5 to 10 to the power 6. So, well, here it is even coarser resolution. So I think in these simulations is that it does not make sense to have a 100 solar mass black hole, because even if I put it in one time step, when it accretes one gas particle, it will become larger than these supermassive seeds. So I would say that these simulations are limited by the resolution. So for example, 10 to the power 6 or 10 to the power 7 is the lowest one that we can resolve in these simulations.
Okay, thank you.
So, Reinaldo, you also have a question?
Yes, thank you, Paramita. It was very interesting talk. Yes, I had one question very similar to Juan's about this mass of the seed. I saw also in this last plot you were showing that the simulations where you started with seeds with mass of 10 to the power of 2, you start it earlier in Redshift 25.
Yes.
So it's also dependent on the initial time of your simulation, this seed, or?
Yeah, it's basically depends on the resolution. The initial time is always Redshift 1000.
Okay. You just are showing from that. Okay.
Yeah, because here
right.
The initial time depends on when the halo will become higher than the mass. This is again a parameter that whenever the halo becomes higher than a certain mass, I put a black hole of certain mass at the center. And depending on the box size, the size of the box, the resolution, this may happen a little bit earlier, or this may happen a little bit later. Yeah. But it is only like Redshift 20 is between 100 and 200 mega year, and this few hundred mega years, because at this Redshift, the time and Redshift are different at such high epochs and at low epochs. Yeah. So.
I see. And I have another short question, if there is nobody. It's about the quenching of the star formation. So the physics, you interpret that it's an effect of the temperature. Because of the feedback, the temperature is higher in the gas of the galaxy. Is it so, or it's because there is more kinetic energy in the gas?
I think there is effect of both. That there is high temperature, but I think in the star formation law, it does not depend on the temperature. So, well, even if there is an effect of the temperature, the way in which is implemented is that gas will then have a higher velocity, so it will expel the gas around it, and it will basically reduce the density. So the way in which is implemented in the code is through the density, the star formation. And so I think the temperature only has an indirect effect on this.
I see. It's the density and possibly the kinetic energy.
Yes. So the temperature, then it gives the velocity, yeah, and then the kinetic energy, and then there is density. Yes.
I see. No, thank you.
Yeah.
Because also I guess that the kinetic energy you also will have plus magnetic energy density proportional to the kinetic energy density, also helping to quench the star formation. Is it so?
Yes, this is actually a very good point, and Selenia is supposed to. So now we are almost doing this MHD simulations. So now we are taking into account the magnetic field, and if the effect that you mentioned is present, then I think in the gadget MHD runs, we should see this, that the star formation is even lower than in a run with no magnetic field.
Thank you.
Yes.
I have a very basic question also related to this subject, but it's very basic. How actually do you calculate the star formation rate? How do you estimate this?
Yes, so I do not have a slide on this, but there is again this. It is called a subresolution subresolution physics. So you remember this kind of equations that we compute the accretion rate. So similarly, we assume this Springel and Hörnquist model. Springel and Hörnquist 2003 model for the star formation. So it depends on the density of the gas, And there is again a parameter which is kind of tuned to the observations at the current epoch to see that if there is gas of certain density, then it should form that amount of stars. So as I said, like it is a sub-resolution because we do not actually resolve the star formation. So one of our gas particle is a stellar population because it is 10 to the power 5 or 10 to the power 6. So we assume that many stars are forming together, and for the details, I should look into this paper and then, because I do not remember right now. But it depends on density. Yeah.
Okay. Okay, thank you. So is there any further questions?
I have another question. So Paramita, do you think to advance more in the studies, what's you need is more resolution from now, or do you think there are some process that needs some refinement in the modeling, maybe other ingredients, or just a matter of study parameters, initial conditions, and the ingredients are all there?
No, definitely we need both, because these two are like complementary. And of course we need more physics, like magnetic field, for example. Then I do not have any kind of radiative transfer, which is very important to see like the smaller scale, that how the radiation from the black hole is being coupled to the surroundings. So in that case, sometimes radiative transfer can be very important. But again, it depends on the resolution, because if we do not resolve certain scales, then maybe the physics is not important. So it could be that in the moderate resolution, even if I put in some physics, the results will not change. So probably as we go to higher and higher resolution, we will probably need more and more physics to be included, so that to make it consistent with the observations.
The cosmic ray pressure could have an importance. I don't think so, right? In these scales, maybe only inside the galaxy, maybe it could have some importance for this.
Sorry, what pressure did you say?
Cosmic ray pressure could have some importance, maybe to the star formation recipe.
I think probably at smaller scales, or I don't know. Yeah, these studies are always a compromise between the resolution and the physics that we can probe. Yeah.
There's another question.
Paramita, one more short question. This has to do with what you were talking with Betchy. Probably you were talking about the final parsec problem. And in your simulations, you showed that there are some behaviors that indicate when two black holes merged. So, but you did not specify what is like the analytical prescription that you follow to decide when you have a merging.
Yes. So I do not have the equation, but each black hole has kind of a smoothing length associated to it, which is also the length that is used to smooth the quantities. Like when we calculate the accretion rate, we kind of smooth around the neighbors of the black hole. So yeah, there is a smoothing length associated with the black hole, and we assume that whenever two black holes come near each other such that the distance between them is smaller than the summation of the smoothing length, then they are like touching. And we assume a velocity condition that it is not moving at higher than the sound speed, and then we allow the black holes to merge.
Okay, thank you.
But this moving length is again of the order of kiloparsecs. So yes, we merge black holes from kiloparsecs.
Right. So no, the question was more in the sense that if these were kind of consistent with the final parsec problem.
Oh, no, we have nothing to do with the parsec. We are kiloparsec.
Okay. So probably I think this is a very strong assumption.
It is a very strong assumption, yes.
Thank you.
Okay, so I think if there's no further question, we can stop the transmission and we can still continue here in the meeting.
Thank you again, Paramita.
Yeah.
And everyone.
Thanks for inviting me. It was nice.
Thank you.